Okay. What I'm going to do now, I'm going to go again over the concept of relative stability, the gain margin, and the phase margin. If you remember, we said in Rauther-Wills or in general, if I have two systems, okay, with the pole of this system, system B, are near the j omega axis, and system A, where the poles are far away from the j omega axis. Which system will be more stable?
The system A, of course, which is
Of
far away
course, system
from.
A is far away, the pole.
Yes.
Now the question is, I mean, before I will relate it to the Nyquist, why we worry that much about this is close and there might be instability? Where
Yes.
physically, how does that happen? I mean, if
Yes.
we have the system here, the poles are near the j omega axis, but they are not on the j omega axis.
Yes. So we worry actually, doctor, because if we want to increase the gain or a certain parameter, or even if there is a perturbation in the system of this kind of a noise or something, this might drive the system to instability. So it is really dangerous. We need to know the margin that we have the freedom to, for stability.
Well, you are almost perfect. One more thing. Now, usually in the design, you design mathematical model. You build a mathematical model. When you want to take this mathematical model and make it physical system, workable system, you might have, some of the parameter is not what you have put numerically, which means there is the parameter you mentioned that there is a change in the parameter in the system, which might lead that the system become unstable. So that's why, as you said, we are worrying about the how far we are from the j omega axis. Now, I would like to relate this one, the position, to what we have done in Nyquist. Okay, those two systems. Suppose I have, okay, so basically in the Nyquist, which one of those correspond to the case where the pole near the j omega axis?
The right one.
This one.
Yes.
Because now we are close to the -1. And we said in the Nyquist stability criterion, we are worrying when we will be encircling the -1. So the more near to the -1 point, the more instability. Okay, so this one definitely, this is far away from -1. So this system is more stable than this one. Okay, and this is the concept of the gain margin. That's basically, I look into this point, what is the factor that I will multiply this point so that I will pull it and make it here. Okay, so this is the concept of gain margin. Let me also, okay, relate this one to the time domain, because look, the time domain is what's important to us. We would like to see, we do the design, the frequency, but always what's important, ultimately, we are living in real time. So we should know in the time domain. So let me compare those situations. Okay. First of all, okay, before we do that, now we have the three cases. And here the system is, what can you say about stability of the system? Let's say system 1, system 2, and system 3. What can we say about the stability of the system? Wait a minute. Let me check now if, as I said, Abdurrahman, everybody is around. Well, somebody just Abdurrahman Al-Muhammadi. Al-Muhammadi. Okay. Now tell me. I have system 1, system 2, and system 3. Which one is stable? Which is marginal stable? Which is unstable?
We have one is unstable.
Which one unstable?
Number one, unstable.
Okay.
And number two, marginally stable.
Okay.
And number three, stable.
No. You reverse them. Look. This is the positive frequency. Okay. If you take the negative, it's going to be something like this. And somehow, so basically, the -1 here, this is not enclosing the -1. Okay, which means that my system is stable. And this one, 2, is passing through the -1. So the system becomes marginally stable, while 3 will be unstable. The -1, okay, can somebody tell me the -1, if I want to relate it to the location of the pole of the system in the S-plane? Can somebody tell me where is it, if this is the S-plane, where is the -1? Where will be the location of the pole of the system?
On the G omega axis.
On the J omega axis, which means that the system is going to be purely oscillate or marginally stable.
And damped.
And damped, yes. Okay, so this is basically, this is the case. If the system,
and Doctor, on the body plot,
okay,
it will be 0 dB and -180.
Exactly. This is if you are talking about the body plot, let's say. So this is the -1 because the magnitude will be 1, and in the body plot we are taking 20 log of the magnitude. So if this is 1, 20 log of the 1 is going to be 0, which is going to be the 0 dB line. Okay, this is 0 dB. This is, let's say, 20 dB. This is 40. So the 0 dB, this is the 0 dB line, which is again to the -180. Yes, correspond to the angle of -180. Okay. Now let me relate this one into the time domain. Okay. The first situation, suppose I have, this is the intersection of the polar plot with the real axis. I'm intersecting in here, which is far away from the -1. This corresponds to, in the time domain, this type of response. The system is stable. It will overshoot a little bit, and then it will go to steady state. So, look, what we want to do, we would like to relate the Nyquist to the location of the poles and ultimately the system response, because always we care about the time domain. This is the impulse response of the system. The other case, look, I'm moving near to the -1. So the oscillation will be more, but still the system is stable. So the relative degree of relative stability, definitely case A is more stable than case B. Now suppose I pass the Nyquist through -1. How does the response look like? If the Nyquist passed through the -1, we said the poles of the system are going to be on the J omega axis, and I'm going to have pure oscillation. The system is, case C will be the system will be marginally stable. Okay. Now, if I intersect beyond the -1, and beyond the -1, the system clearly becomes unstable. the response is growing. Any question here?
Jamil. So, Doctor, can we now kind of have a measurement for the gain margin and the phase margin?
Exactly. What we want to do,
and also the crossover.
Definitely, because look, to get the measurement, you need the crossover. So basically, look, if this is the okay, and let's say this is the -1, how much I can multiply the gain at this point? Look, the gain at this point, well, by intersecting the Nyquist with the real axis, which means that what's the angle will be at this point if you are taking the polar?
Minus 180.
If you are taking Cartesian representation, what do? You set what? The Cartesian, okay, let's say G of J omega equal A plus J B. What do?
Yes.
You set B equal to 0, which is
and A negative.
And A is the negative.
Right.
Yes. No, but setting B equal to 0, that will give you the frequency. That will evaluate the frequency, use this frequency and find what's A. Automatically, definitely, it's going to be in the minus. Or if I set it to be 180 degree, minus 180 because I'm moving in this direction, okay, that will give me the frequency. I will use the frequency to find what is the omega in here. Then, what will be the factor? Okay, let's say this is X, and this is the magnitude is A. I need X times A equal to 1. So, X, the factor will be 1 over A. 1 over the magnitude evaluated at this point. And this is my measure. How far I am from the -1. This is what we call the gain margin. So let me define it precisely. The gain margin is a change in the open loop gain expressed in dB required at -180 degree of phase shift to make the closed loop system unstable. Because when I pass through the -1, my system, even though we can marginally stable, but let's say this is the verge of stability.
Yani can we say, Doctor, for example, in the body plot, because I think we have a question in the homework about this. I think it's the first question. Can we say that it is the K or the gain that is needed to drive the system to larger than 0 dB at -180?
Exactly.
I see.
So this is basically, look, the procedure to find the gain margin. First of all, this is your plot. Take this point and take the phase of this point equal to 0. No, sorry, to -180 degree. And that will give me what we call this point where I cross this, at this point when I cross the 180, I will say this is the phase crossover frequency. So the phase crossover frequency, the frequency at which the phase is going to be -180 degree. A phase crossover frequency of the GH of J omega is a plot, is a point at which the plot intersects the negative real axis. Then the gain margin, this is, okay, this is the way I find omega, the phase crossover frequency. Okay. And this is basically, once I get the frequency, I substitute in the magnitude and take the inverse of it. That will give me the gain margin in, just gain margin. In dB, take the 20 log of that quantity. Now, if you are working with the body plot, okay, In the body plot, we look into the minus 180 degree. And let's say I'm intersecting the phase in here. So I will take, this is my frequency. This is the phase crossover frequency. We are going to come to the body plot a little bit later, but you know, if you want to relate them from now. Okay. So
And in the magnitude, we look to the 0 dB, right?
no, in the, wait. In the phase crossover frequency, now the phase crossover, it means
Yes.
the phase should be minus 180 degree.
Right, because it will have -1 at the denominator, and then it will result in infinity.
Other one, the other frequency we call it the gain crossover, that where the magnitude equal to 1. But now let's focus, Abdurrahman, let's focus on
تمام.
the gain margin. So this is the gain margin. Any question, Shabab? This is the formula. How do we calculate? Any question? Okay.
يعني دكتور الجين margin we calculate it at the phase crossover.
Yes. We find,
تمام.
first of all, okay. To find the gain margin, find the phase crossover. Find this one. This is 0.1. This is 2. Find, okay, find omega c such that the angle is going to be 180 or minus 180, because look, if you are moving in this direction, it's going to be minus 180. Okay. And then once you get omega, substitute in the magnitude and get the, and take 1 over the magnitude. That will give you the gain margin. Take 20 log of that quantity. That will be in dB. Okay. Now, the phase margin. Before we go to phase margin, why we, okay. The question is, since I have the gain margin, is it enough to determine the stability of the system?
No.
Why not?
I think, Doctor, because in some cases, you need actually the the phase margin or to you know, I don't have.
You are right. I'm coming to it. Okay. Okay. Look, the gain margin, okay, is one-dimensional representation of the relative stability. Unfortunately, gain margin alone sometimes is inadequate to indicate the relative stability of the system. Because look, suppose I have the following situation. It's a weird situation, but it could happen. I have two systems, system A and system B. What is the gain margin of both systems?
Same.
They have the same gain margin because they intersect the real axis in the same point. But which one is more stable?
The A, of course.
The A. Because in the B, there is a possibility I'm near in this area, I'm very close to the -1. I could cross the -1 and my system become unstable. So the gain margin by itself is not enough. So we will go to another concept of phase margin. In the gain margin, we said, okay, where does how do we have the phase margin? The gain margin, we know that you increase the gain in the system. What about the phase? How does the phase, where does the phase will come from?
We actually assess how far we are from the -180.
No, but physically. How
Physically.
How do you get them? We know K multiplied by pure gain multiplied by your system, and it will give you. The phase, it will come, sometimes certain component in the system. Suppose I have, and that where when
storage element, Doctor.
Compensator, okay. For example, if I have a circuit, okay.
Yes.
Capacitors in the system.
Any storage element.
Energy storage element. So suppose I have, let's say,
yes,
I have S plus A and S plus B. Okay, what will be the, what will be the phase of the system? Or this is J omega plus A, and this is J omega plus B. Okay, so the phase will be of the system will be tan inverse of omega over A minus tan inverse omega over B. So definitely A and B will determine the phase in the system. And those, they might lead to the, problem with the phase margin, or how do I, fix the phase margin. And this comes from circuit. I could have a circuit which will do the job for me.
Yes, Doctor, like what we have studied in the 213, in which the current is lagging or the is leading
Exactly.
the capacitive load and the inductive load.
Exactly. This is very similar. So now, okay, the gain margin, we said, how much gain I can add to the system before I will reach the -1. Along the same definition, how do we define? Let me try. Turkey.
Yes, doctor.
Okay. In the gain margin, we said how much I can add gain to make the system go to the -1. Along the same concept, how can I define the phase margin?
Not sure, honestly.
What?
I'm not sure.
Okay. Any help, Shabab? Thank you, Turkey. It is concept is new. I'm not, I'm not testing. I'm just to,
Yes, Doctor. So
on board.
The phase margin, we will find the phase and then we will add plus 180. Why?
So no, the phase margin
is the difference between minus 180 and the phase that you are at.
Exactly.
And so what we will be doing.
No, and the phase of the system.
Yes, the phase of the system.
Okay, in the gain margin, we find this point.
So we subtract minus 180, and then so we will add 180.
So basically, okay, let's define it. So basically phase margin, it has to do with the phase. How much phase I can add to my system before I reach the instability. The phase margin is a change in the open loop phase shift required at a unity gain now that make the closed loop system unstable. So basically, let me look at it in here. This is my body plot. My Nyquist. I want to evaluate the gain at, I would like to evaluate the phase at a unity gain. So basically, look, this is my system. Okay. And suppose this is the -1. Let me draw a circle of the center of the circle in the origin, and it will pass the -1. What will be the radius in here? What will be the radius?
1.
And so basically it intersects. So basically at this point, what will be the magnitude? At this point what will be the magnitude? The circle or unit circle is intersecting my graph at this point. So what will be the magnitude at this point?
Magnitude always 1.
Not always 1. No, at this point only. Not every.
Oh yes, I see.
So in here,
I mean everywhere on the circle, on the
yes.
Yes.
Yeah. So it will intersect in here. So this is basically where we call the gain crossover frequency. So I define now, okay. I define this point. This is the point. the gain crossover frequency.
In the body plot it's
No,
zero.
this is no.
Yes, right.
Gain. This is the gain.
لا هو حط الفيز.
لا انا نقلت شو اسمه انا
الفيز.
it should be the gain. I will change this slide.
تمام.
Okay, I worked on it yesterday.
دكتور هذه equivalent ل 0 dB صح؟
This is the 0 dB point. Okay, so I evaluate. This is the this is okay, gain. Okay, crossover frequency omega C G gain, crossover gain. Okay, and then use this one to evaluate the phase in here and calculate. This is the direction for the phase. Calculate. This is PM is the okay. The phase margin is 180 degree plus the phase at omega CG. So basically we are calculating this one and then how much I need to go to the 180 degree. And that's why this is basically my phase margin. This is the way I evaluate my phase margin. Any question before we go to?
Basically we add here 180 because we subtract minus 180. So this is kind of adding 180 to see the difference.
Look,
yes.
This is the positive direction of the phase margin from this point. Okay, let's take an example. Find the gain and the phase margin for a unity feedback system. By the way, one more thing. Think about the phase margin. Later on, we are going to relate the phase margin, in particular for second order system, to zeta.
Yes, of course, because when you increase zeta, I think you might drive the system to instability.
Yes. So basically, we would like to, we don't want to have them just mathematical, figure. We would like to have sense of what we are doing. So the phase margin is related to zeta, which means it's related to the percentage overshoot of the system. As you said, if zeta equal to 0, you will have more oscillation. Okay, so let's take this example. First of all, let's sketch quickly the Nyquist, and then we talk about the gain margin, phase margin. Okay, so let me locate the pole of the system in here. How many poles I have?
I have 3 poles.
3 poles. This is at -2, and I will have this will be complex somewhere in here.
Yes.
So if I take my Nyquist contour along this line, okay,
B equal to 0.
P equal to 0.
And then we go to the F of
G
S plane.
of J omega.
Yes. Have here the 0 minus
6 over minus J omega square plus 2 J omega, okay, plus 2 multiplied by J omega plus 2. In terms of the magnitude, what will be the magnitude?
we have
Wait a minute. Let me simplify it a little bit more. Okay. So
no, we can do it here.
well, I know
4 plus omega square.
Let's do it. Okay, minus omega square plus 2 J omega plus 2, and this is J omega plus 2. So this is equal to the magnitude.
The magnitude is square root omega square plus 4.
2 minus omega
ماشي.
square plus 4
omega
omega
square.
Then I
multiple
uh,
omega square plus 4.
omega square plus 4.
The phase
Phase will be
minus tan inverse of the 2 omega over 2 minus omega square minus
tan inverse
omega over 2.
omega over 2. Now let's
Yes.
sketch. This is the G of
Now we want the to find the gain margin. We want omega cross.
no, first of all, okay, no, before the phase margin and gain margin, let's just sketch it. How does it look like?
طيب ممتاز.
What's the G of 0? G of 0 شباب, okay.
0 plus or 0.
I don't need, look. We use 0 plus if I have a pole on the J omega axis. I don't have any pole on the J omega axis. I will use 0. Look, this is, I don't have any singularity on the J omega axis. I don't have any problem.
تمام صحيح.
Okay. So let's have some of you.
0.
Just 1 second. منتظر.
Yes.
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 Tell me, what will be the magnitude when omega equal to 0?
Is it 0?
What? It will be what?
Is it 0?
No? Just substitute. This is 6. I'm talking about magnitude. This will be what? This is 6 over. This one will be 0. So 2 to the power 2 and the square root will be 2 times. This is 0. So it will be 2, another 2. Okay. And the angle will be, what's the angle? Now the angle will be 0. This is 0 and this is 0. So it will be 0. So basically what I have, shukran. Okay. So basically I have the magnitude is going to be 1.5 because this is location. This is 0. Now let me take the other extreme, J infinity. Okay. So at J infinity, what do I have? What's the magnitude? Shabab, what's the magnitude?
0.
0. Angle? This will give you what?
Minus pi over
Minus 1.
This is minus pi over 2. How about the other one? This one?
0.
No, 180. Because of the minus sign here. Okay, there is a minus sign. So it's 180. So minus 180 minus 90, which is going to be 0, an angle of minus 270. So basically, this is the way it's going to be. And then the, okay. Assume this is the minus 1. Now I would like to obtain what is this point to determine the gain margin and the phase margin and the stability of the system. Okay. Look, this is the neatest plot is this one. This is by using, MATLAB. This is the minus 1. And this is the, okay, 1 point, this is going to be, sorry. We are talking about, I'm talking about this point. This is the 1.5. Okay, this is the starting point. Go this way and take it and come back. Okay, now I want to find the gain margin. So what do I do? What do I do?
We have to find the omega crossover.
Okay, which means that what do I do? I have to set the angle
Minus 180, yes.
minus 180.
And then we find the magnitude at this
Okay,
omega.
exactly. Once, okay, this is, if you remember, okay, if you remember, we said there is a formula, tan inverse of x plus tan inverse of y equal tan inverse
Of x plus y over
plus
1
y
minus
over x,
1.
sorry, 1
1 minus
xy.
xy.
So let's apply it in here and multiply by minus 1. I will have tan inverse of, this is 2 omega over 2 minus omega squared plus omega over 2 over 1 minus 2 omega 2 minus omega squared times, omega over 2. This is equal to 180 degrees.
So the 2 omega over 2 minus omega squared plus omega over 2 equal to 0.
So basically, the tan of the 180 is equal to 0, which means that the numerator must be equal to 0.
Yes.
So if I clear, so this is what I'm saying. Solve for it now. If you solve, you will get omega equal to root 6. Look, possibly we'll have another omega, because this is, it will be what? Second order system. Okay, the other one either 0 or is going to be negative, so we ignore it. So we'll take the omega equal to root 6. Okay. Now,
Yes.
what do I do?
Now you go to the formula. What we have 20 log.
Now you go to the gain.
The gain, yes.
Yes. Okay. Okay, so now you set the gain. Okay. You set the gain 6 over root of this one equal to, evaluate at root.
Omega equal root 6.
Root 6. Look, there's one thing you could do it differently. And here, look, I use the polar. In here, we have also the Cartesian, if you want to. How do you get the Cartesian? The Cartesian, simplify in here, multiply by the complex conjugate, so you'll get this one. So clearly, if I want to use this one, what's omega will be?
Root 6.
Root 6, because, you need this one to be 0. And then substitute in here to get the real part, and that will be your gain margin. Or the way we are doing it, so let me substitute in here. Let me substitute in here for omega equal root 2. If you do that, the answer for that one is going to be 0.3. The magnitude, the magnitude at omega equal root 6 is going to be 0.3. So the gain margin is going to be 20 log of 1 over this quantity. This is your gain margin, and the system is stable. Because look, in term of this encirclement, it means that this is the 0.3 and this is the minus 1. This is minus 0.3, let's say, and this is the minus 1. It means that I'm not encircling the one, and my system is stable.
You need kind of a gain of 10. Of course, it's a gauge gain, or the difference to reach to instability.
Yeah, the verge of instability is that basically this is, if I up to this point, if I multiply my gain Up to this point, the system is stable. Beyond this point, let's say 11 or 12 or 13, the system becomes unstable. So this is the verge of stability. This is the maximum which I can put in the system before the system becomes unstable. Okay? Now, let me find the phase margin. How do I find the phase margin? How do we find the phase margin?
As we have stated, we find the omega crossover for the gain, which
So
is the
basically, what we are saying, this is the gain. This should be equal to 1 to get the gain crossover frequency. Now, this equation definitely is going to be complicated. It's going to be of what? Which degree?
that might go
Degree?
4th degree.
Degree 6.
Yes, right.
Because this is 4 and multiply by 2. Solve it. Well, phase margin, find the frequency at which G has a unit gain. Using a computing tool, MATLAB or your calculator, you can find the frequency. The frequency is going to be 1.251. Substitute in the phase angle, you'll get the phase angle is going to be 112.3. Okay, then 180 plus this one will give you the phase margin, which is 67.7. If we do it in the body plot, it will be easier. But again, the problem with the body plot, to plot the body plot is not going to be that simple. Any question? Any question, Shabab? Okay. Well, next time, okay, we will start and relate the phase margin, as I said, to get the phase margin in terms of the zeta of the system, because when we go to the design always they will ask for, specify certain phase margin. So I have to relate the phase margin to zeta directly. Okay, and that's what we will do for the second order system next time. Okay, so thank you, and we'll stop in here. Okay.
دكتور بالنسبة للواجب البودي
أيوة.
بلوت أول سؤال هو كلها على الريلاتيف ستابيليتي على الفيز مارجن والجين مارجن.
Well, fine. We will still have يعني الhomework due next Sunday.
Yeah.
To do it.
So
But
no problem يعني.
Tomorrow quiz, no. Tomorrow quiz definitely phase margin, gain margin, body. Just body without phase margin, gain margin.
So it will be just, kind of drawing the four cases, the gain and the real axis and the complex and all of that stuff. Yes, I see.
Until now, I did not set the quiz. I will do it today, inshallah.
Mm-hmm. But this is good, yani. For that reason, I know the phase margin and the gain margin before the class, because when I started solving the homework, I was stuck.
Anyway.
So yeah.
Well, yeah, it is. I used to give the phase margin and gain margin with the body plot. Now I changed the system because I believe.
But it's not hard, doctor. It's the same concept, yani.
Yes.
It is the, yani.
Yeah,
it is.
Yeah, it's the same but different approach. This is basically
Because